guys. So the last factoring method that we're going to go through here, there's actually two of them. The first one I want to talk about is what I call the AC method. We're going to use that when the leading coefficient in a trinomial is not 1. So as I told you guys last week in our Zoom meeting, that the unfoil method that we used was for trinomials, 3 terms, where the leading coefficient is 1. So now we're talking about if it isn't 1. So this is what the trinomial would look like. Ax squared plus bx plus c. A, b, and c would just be real numbers. And we're saying a isn't 1. Okay, so you're going to see a number there other than 1. So we cannot use the unfoil method. So we're going to use what's called the AC method. And again, as I mentioned last week, it's kind of a combination of what we do in the unfoil and what we do in the grouping. So in this first example here, this is a trinomial. The leading coefficient is not 1. First thing I'm going to do is look for a GCF. There is no GCF here. So the next thing I'm going to have to do, because the leading coefficient is not 1, I'm going to use what's called the AC method. So it's called AC because, again, A is the coefficient with x squared, C is the constant. AC means A times C. So I'm going to multiply A times C. So 3 times a negative 5. And that gives me this negative 15. And now I'm going to ask the same questions I did in the unfoil. What multiplies to a negative 15 and adds up to the middle coefficient? Okay, so when I come up with those two numbers, negative 15 and 1, I multiply them just to make sure. It gives me a negative 15, and I add them, and it does give me a negative 14. So now what I'm going to do, in the unfoil, this would be my answer, but this isn't unfoil. So what I'm going to do is I'm going to take these two numbers, and I'm going to rewrite this trinomial as 4 terms. So you'll see I used a different color here to kind of point out what I did. The first term and the last term are going to stay the same, but I'm going to rewrite this middle term, this negative 14x, as a negative 15x plus 1x, because a negative 15 and 1 were the two numbers that I came up with here. So you see I'm not changing the value of this problem at all, because if I were to combine these, I would get negative 14x. But the reason I'm writing it as 4 terms is now I'm going to factor by grouping. So I show my brackets here to show what I'm grouping together, the two terms. So I take the GCF out of the first group, which is 3x. I divide each of these terms by 3x to get what's left in the parentheses. Then the GCF of the second group is just a positive 1. So I take a positive 1 out, I divide, and this is what I'm left with. We can see the parentheses are the same. So I'm going to factor again. The GCF just happens to be the x minus 5. That comes out. And my parentheses is what I'm left with, the 3x plus 1. So I just finished. I factored this trinomial, whose leading coefficient isn't 1, into these two factors. Okay? Again, you can check it by foiling, and you'll see that you should get what you started with. Okay, so example 2 and example 3, they're taking you kind of through the same thing. The only difference is I wanted to point out in example 2 that there is a GCF here. So I'm going to take a 2 out, 6, 2, and 8. They have a 2 in common, so I took a 2 out. And then this is what I'm left with. And notice I just wrote above, this is A, this is B, B is 1, and then C is negative 4. So again, I asked the two questions. What multiplies to 3 times negative 4, which gives you negative 12. So it multiplies to a negative 12 and adds up to this negative 1. I come up with my two numbers, and then I rewrite this trinomial as 4 terms using the negative 4 and 3 in place of this middle term. If I combine these, I would get that negative 1a. But now I can factor by grouping, and you can walk through that and see. And then the last thing is you got to remember to bring that GCF down. If you take out a GCF, just make sure you write it in your final answer. Okay. I have a little note here. Be careful because, again, when you're thinking what multiplies to a negative 12, well, a negative 2 times 6 could be a negative 12 as well, but those numbers wouldn't add up to a negative 1. And so that's why what I talked about last week, again, when you write the two numbers, multiply them again to make sure they multiply to what you wanted, and add them to make sure that they fit both criteria there. Okay. Example 3 over here. Just another example, there's no GCF here. So again, what multiplies to 12 times 1, so what multiplies to 12 and adds up to a negative 8. I have my two numbers, and then I rewrite it as 4 terms, and I use grouping. Okay. I put another little note down here. Sometimes when I give you, when you see polynomials, they're not factorable at all. So this is why you have methods, because you go through the different methods. So if you look at this polynomial here, there's no GCF, okay? It's a trinomial, and the leading coefficient is not 1, so really the only method I could try is my AC method. So what multiplies to 2 times -1, what multiplies to a -2, and adds up to 6. So as I think about it, nothing will, okay? And so no two numbers will work, therefore this is not factorable. And a lot of times what you'll see for something that's not factorable is they'll write that it's prime. It is not factorable, okay? So that's the AC method. The last method I want to show you has to do with some patterns to recognize. And so here's the two I taught, and again I talked about these last week. So the first one's called the difference of two squares, and it's all in this name. Difference means it's a subtraction, and then two squares means that the two terms are perfect squares. Okay, so it's a subtraction of two perfect squares. So it would look like this: a squared minus b squared. You can factor a difference of two squares. It's going to factor to two parentheses. One's going to be a plus, one's going to be a minus. And the numbers that go in here are going to be the square root of each of these perfect squares. Okay, so if you look at example 1, x squared minus 4. Now again, I'm going to look for a GCF. There's no GCF here. But I notice it's two terms now. There's a subtraction. It's two terms. So far I have part of these. And both of these are perfect squares. So what I tend to do is just underneath it write what the square root is. So the square root of x squared is x, and the square root of 4 is 2. So I'm going to put two parentheses, and these are going to be the two terms that go in there. So x plus 2 and x minus 2. And it doesn't matter if you put x minus 2 first or x plus 2. That doesn't matter. So that's what this little note here. If you look at example 2, there's no GCF here. It's two terms. There's a subtraction. The square root of 4x squared is 2x. The square root of 25 is 5. So these are the two terms that are going to go in my two parentheses, and you're going to put a plus in one and a minus in the other. Okay. Example 3, I happen to have a GCF here, so I took a 2 out. And then if I look at what I'm left with, it's two terms. It's a minus sign. Square root of 4x squared is 2x. The square root of 9 is 3. So those are going to be my two terms, one a plus, one a minus. And just make sure you bring that GCF down. Okay. In example 4, I'm showing you, okay, here's two terms. And hey, they're both perfect squares. The problem is it's a plus, not a minus. It's called a difference of two squares, not a sum. So if it's a plus sign, there's no GCF. The only method I have for two terms would be if it's a difference of two squares. This is not, so this is prime. Okay, it is not factorable. Okay, and then the last pattern I want to show you has to do with trinomials, and it's called a perfect square trinomial. And so I wrote in here the first and the third term have to be perfect squares, and the last sign has to be addition. So here's an example of what it would look like. There's no GCF here, but if I notice, this is a perfect square, x squared. 49 is a perfect square. And the last term here is a plus, but there's actually one more thing that has to happen. So what I do is I take the square root of the first term, I wrote it underneath. The square root of the last term, of 49, is 7. And always put a 2 in the middle. That's the pattern. There's got to be that multiplied by 2. If I multiply straight across, x times 2 times 7, it gives me 14x. If this is the same as the middle term, then I know I have a perfect square trinomial. And to factor it, notice what I circled here. I take the square roots of those two perfect squares. That's what goes here. You take the sign of the first sign in the problem, happens to be a plus, put it in parentheses, and it's squared. Now again, if you want to check that, you could write it out, x plus 7 times x plus 7, and you'd be able to see that you get this x squared plus 14x plus 49. Okay, here's another example. Excuse me. There's no GCF. And again, you could, when you look at this, if you unfoiled it, because leading coefficient is 1, it will still work. But I'm going to show you this pattern that you can notice. The square root of this is perfect, so the square root of x squared is x. Square root of 16 is 4. Put a 2 in the middle. Multiply straight across, it gives me 8x. Well, that's what my middle term is. That means it fits my perfect square trinomial, the pattern. And so I notice what I circled. I circled what my square roots were of my perfect squares, and I write them in parentheses. I use the sign, the first operation sign in that polynomial, and then I just square it. Okay? Example 7 over here, and this is good reason why knowing this pattern can be helpful. There's no GCF here. The leading coefficient isn't 1. So if I wanted to use the AC method, I would have to figure out first what is 9 times 25. It's going to be a larger number. And you'd have to figure out what multiplies to that product and adds up to negative 30. And that might be a little bit harder to do. But what I do notice is that my first term here is a perfect square. The square root is 3x. The last term is a perfect square. Square root of 25 is 5. There's a plus sign at the end, so I'm good. When I put a 2 in the middle and multiply straight across, it gives me 30y. Well, that's exactly what my middle term is. Therefore, this is a perfect square trinomial. So the way it factors, I take the square roots of my perfect squares, the 3, sorry, that should be, I don't know, I have an x and a y, sorry about that. This will make it a y. So this will be a 3y, and then a 5. I use the minus sign because that was the first operation sign, and just put in parentheses squared. So recognizing a perfect square trinomial can make your factoring easier. It will also help you with something you're going to be doing with quadratics in Math 2. It's going to be very helpful to be able to recognize them and understand what they are. So practice with it. Now, I gave you an example here of one that is not. So when you look at this, you're thinking, hey, it's a trinomial. X squared is a perfect square, and 16 is a perfect square. And you're right. The problem is this minus sign at the end. It's never going to be a perfect square trinomial. A perfect square trinomial, the first and third term have to be perfect squares, and the last sign has to be addition. If you have that, then you're going to go through what I showed you in these 3 examples, where you find those square roots and then you put the 2 in the middle and see if it works. Because sometimes you put the 2 in the middle and you multiply across, and your product is not the middle term. Well, if it's not, then it's not a perfect square trinomial, and you'll have to try another method. This is just a pattern that you could try to look for right away. And if it doesn't fit the pattern, then you're going to fall back on some of your other factoring strategies. But if it fits the pattern, then you're pretty much done with the factoring. You have everything you need. Okay? So those are the last 2 that I wanted to show you there. So just make sure that you take the time to study the notes, to really study these examples, so that when you try the worksheets on your own, you can see how you do with those. Okay? All right. Good luck, guys.